Welcome to Maths with EJD. In this video, we'll be talking about spectral analysis of audio stroke music signal spectrum. So in the last two videos, I talked about spectral analysis of temperature variations. Then I talked about, after that, I talked about spectral analysis of mechanical vibration signals. So this is the last video in this series, except some other things comes up and I need to make other videos. But with this, I'm bringing this playlist on spectral analysis to a close as we look at spectral analysis of audio stroke musical signal spectrum. Okay, so again, we follow the pattern of, of course, the whole idea of spectral analysis is to bring something from the time domain into the frequency domain. So as usual, we'll take our time series. Well, in this case, we are dealing with some kind of audio file. So in this case, normally, so we take it from the time domain, right? Then we preprocess it and take it into the frequency domain, and then we do spectral analysis and get some interpretation out of that. But we are dealing with music or audio. So in this case, at the end of what we'll be doing is, you should have been able to acquire or curate audio at appropriate sample rates and levels. Then you can gain you can have gain or bit depth, right? Depth. Then clean and prepare signals, maybe mono stereo handling, normalization, resampling, DC removal, estimate spectra, FFT magnitude, Welsh PSD, STFT spectrogram, MEL spectrogram, and compute descriptors like spectral centroid, roll of flux, MFCCs, pitch F naught, that's harmonic now, harmonicity and inharmonicity. Interpret spectral structure for pitch, timbre, formants, harmonics envelopes, and rhythm or onset with uncertainty and parameter sensitivity. And then we have audio signals and sampling, audio signal sampling and labels. So talking about sampling design now. So when we talk about speech or music, the frequency sample is 44,100 hertz. That's CD standard, or 48 kilohertz for video standard, right? Then the Nyquist limit, you have the highest analyzable frequency to be approximately the number of the frequency sample divided by 2. So ensure anti-aliasing filter at capture to avoid aliasing, right? Then you have the bits there, 16 bits for CD quality and 24 bits preferred for higher headroom and lower quantization noise. So for the channels, now you can have a mono channel used for analysis, stability, and simplicity. Then you can have stereo, which is mid or size decomposition. So for mid, you have M, which is L plus R over 2. Side is S, which is L minus R over 2. And this is used for stereo image or mix of space diagnostics. I remember I was using this software called, what is it now? Audacity. I think it is Audacity for recording audio something. So I know I get to see this mono and stereo kind of thing right there. Okay, mono and stereo channels, that is. Then talking about level and headroom, you can normalize signals to the range -1 to 1 for that's float. Then keep peaks below -1 dBFS to avoid clipping. Then the pipeline overview for decision flow in this case for audio and music file like that. So ingest and sanity check. So sample rate duration. You want to check the sample rate duration, the clipping, the DC offset. Then you preprocess, you convert to mono or M/S or stereo, normalize, optional high pass, 20 to 40 hertz, windowed analysis, choose frame length and hop size, select window hand, and frequency transforms, FFT magnitude slash phase, Welsh pairs, the STFT spectrogram. Then you have musical projections, log frequency or MEL scales, MFCCs, chroma, which is optional. Then you have descriptors and events. So you have F naught tracking, spectral centroid, spectral roll-off, spectral flux, and onset strength. Then for interpretation, you have pitch and harmonics, formants and timbre, percussive versus harmonic energy, mixing diagnostics. Some people will have a better understanding of all these things I'm saying. Then for sensitivity, you can vary window, hop, and FFT size, compare linear versus log magnitude, confirm stability of results. Then reports include figures, waveform spectrum, spectrogram, MEL spectrogram, tables and descriptors, and conclusions. So let's look at a practical guide. So the core libraries, as usual, we have NumPy, SciPy, Matplotlib, and Librosa. We need Librosa for anything involving MEL, MFCC, Chroma, and Pitch. So first of all, we want to ingest mono M/S or stereo. So normalize DC high pass like that. So here we import NumPy as NP, sound file as SF. So here, we are dealing with sound now. So from NumPy, not import numpy as NP, sound file as SF, matplotlib.pyplot as PLT. So it means we can even import multiple libraries at once without having to say import numpy as SP and NP and separately import sound file as SF, separately import matplotlib.pyplot as PLT. We don't have to do all of that. Then from SciPy, you can now import signal. So in this case, we are using a file called audio.wav. So, and I have it, of course, I have it in the this is the playlist for spectral analysis. So you can see the temperature I used for the video before, and then the vibration CSV. This is the spectral. This is the audio now. It's a WAV file. So if I click on it, I don't. Let me see if there's so you can see the sound of the file. So that's what we want to analyze in this situation. Okay, it's a 30-second WAV file like that. Yeah, so that's what the sound is like. It will soon come to an end. Yeah, so that's what we have for 30 seconds. So for the WAV file like that. Okay, so that's what we want to analyze in this situation. Um, that's also I just generated it for this analysis. So we go back to our monochrome, to our collab, Google Colab, since we are using audio.wav. So I just click here. Of course, you see all the files, the temperature and vibration CSV files I had before, they are gone because once that session ended, they ended with the session. So I click this now, then I can locate. So I mean, this is the folder. So I can locate this audio.wav and I click on it. And then it tells me the usual warning, ensure that your files are saved elsewhere. Thankfully, I have my files saved elsewhere. So even if they get lost from Colab, I have no problem because this runtime files will be deleted when this runtime is terminated. So I say, okay. And then the audio.wav file is here now. So because this, we need to access it right here. Okay, so here now we import numpy as NP, then we have sound file as SF. Okay, we've done all of this before. Then this is where we now load the WAV file. Or you can also have other format like FLAC, OGG. So you have X. Interestingly, this file now I can convert it to MP3, MP3, MP4, and things like that. So I have XFS. So SF.read. So to read the file now, you need a sound file. You need a sound file is a library that you need to deal with sounds. So we pick the audio WAV, then we have X shape N or N by 2. Then for the channels now, you now have if X is N.dim is 2, and you have L, comma R to be all these things. So you have this for mid, you have this for side, talking about the stereo thing now. Then you have X is X mono. Else, you say X is equal to X of type float, like this. Then you normalize to, like we heard before, we normalize to -1 to 1, float and remove DC, right? Then we have X equals X, max absolute of X, blah, blah. Then we have the X, which is signal.detrend. So we detrend, we remove the DC. That's like the meaning, right? Removing the mean to make it, to avoid leakage or something like that. Then you have gentle high pass to remove rumble. So if you want to remove the rumble also, we can have that. So we have X's. So let me see if it can, I don't know, if it can generate X for any reason. Let me just put that there. If that's possible for in any way. Okay, so it now gives it out as a kind of array. So it gives us that file now that has been read as X and FS, or maybe I should even read it as X, comma FS2. So you see, it turns the sound into some kind of array. So that's FS, right? So I'm trying to read this X, comma FS. That's the deal. So it gives us this whole array kind of thing. All right. So you see sound converted into like an array. So next we talk about time domain view and RMS peak. So we use this code right here. So we have the time, we have RMS, we have the peak, and then we try to plot the peak. We plot amplitude against time like this. So for the waveform like that. Then we talk about the fast Fourier transform magnitude spectrum, linear and log. So we have FFT length, that's NFFT. set frequency beam spacing. That's delta F is now Fs over NFFT. Then we have zero padding. We have zero padding, which refines display resolution, interpolates, not true spectral resolution, which is set by window length. So in this case now, we have the windowed slice, e.g. 4096 sample center frame. So we have NFFC 8192, window length is half of that, that's 4096. Then start maximum zero length X over 2 and all this. And we have the frame, and then we try to plot some uh, graph. So we have single frame spectrum Han, using Han doing zero padded. So we have the magnitude against the frequency right here. That's us plotting the single frame spectrum. Then we can go ahead and do the Welch power spectral density. So that's average for smoother estimate. So in this case now, we also have all this code in here. I mean, we are used to this already for Welch PSD, and this is what it gives us. So we have some kind of Welch power spectral density. So the highest power is something above -30, like that. And we can also do STFT spectrogram. That's time frequency. So we have, STFT is short time frequent Fourier transform for, dealing with shorter time frames like that. So the frame length here is 20 to 46 microsecond, and this is common in audio, e.g. 10242 2048 samples at 48 kilohertz. And for hop size, we have 25 to 75% of the frame length, e.g. 75% overlap is goes to hop, and then you have to 564 1024 sample frame. And for display, show log magnitude for perceptual clarity. Okay. And we come here again for the STFT spectrogram. We've done things like this also previously. So I just go ahead and run. Okay. So we're dealing with sound this time around. So we want to see a spectrogram in log magnitude where we have frequency against time. So this is the spectrogram in log magnitude like this. So, we have this yellow bands where we have those are some frequencies like that. Then we have the MEL spectrogram and MFCCs, which is optional, and it needs Librosa. So Librosa is another library that we need to use for this kind of situation. So import Librosa, and then we have Librosa. So if it's not already installed, then you install pip install Librosa. So if it gives me an error that I know I have to install Librosa, you have this whole coding right now. And then if it doesn't work, I have to know that I have to install Librosa. So I have a feeling I don't need to bother like that. So it's taking a bit of time. So we're going to have some plotting, MEL spectrogram, and all that. So we have the MEL against the time. Okay, it's taking a bit of time, but waiting patiently to see what it brings. Okay, I hope I don't have an internet issue. I don't think so. Internet is fine, but this is taking so much time. But we are waiting. Okay. Wow. All right, finally, we have it. Okay, so we have the MEL spectrogram like that. So we have the frequency against time, and then we have MFCC 13 also coming out this way. Okay, then we have the pitch harmonic tracking. That's F naught now. Pitch harmonic tracking, ACF or Librosa is also needed here. So autocorrelation, which is simplified for monophonic segments. Okay, that's like one sound segment, if I may interpret that the way I know mono to mean. All right. So here we define a function def f naught underscore ACF. Then we have the frame fs, f min is 50, f max is 1000. That we have center clip and ACF. So x is frame minus. So we remove half of min of the frame from the frame. Then we have r np that correlates x by x and all that. And we do all of these things and we track over frames. I run this and see what happens. So pay attention that Librosa, alternative to Librosa for robust pitch width voicing, you can use pip track or py or pine, to put it that way, pie in. So it's like this sound stuff are taking more time than what we know about temperature variation, and of course, machine vibration signals. So, okay, I mean, this is done. And then we move on to spectral descriptors like centroid, rule of flux, and all that. So we define this function, and all of this is defined this way. You want to look at that more carefully. And then we come to harmonic percussive separation, uh, which is optional, but it needs librosa because effect, you need to get effect from librosa. So we have okay, did I hide it? Then I run this, and then it doesn't show anything, but it runs well, no error. But then we see the visualization in the next cell. Okay, we still have that taking a bit of time. So that analyze YH for pitch and harmonics and YP for onsets and rhythm, talking about spectral analysis of audio and music signals. Okay, taking so much time. Yeah, done. And then we go for the visualization now. So you overlay spectral centroid and roll off on the spectrogram, and then you also plot the F naught tracking using this whole code thing. And I run that, and it takes, thankfully, that's like the last thing to do here. And it takes some time because we are dealing with sound. Yeah, done. And we have the spectrogram with spectral descriptors. So you have the centroid around here, you have the roll-off around here. Then for pitch tracking, you have this kind of thing going on here. So, I mean, with that, we come to the end of this interesting video on spectral analysis of audio and music signal spectrum. Okay, so let me know how helpful this is for you. So, I mean, we've seen applications of all of these things now. We've seen it in finance, we've seen it in biomedicine for, and is it encephalogram or something like that for brainwave analysis, and we saw it for mechanical temperature variation. We saw it for mechanical vibration signals. Now we've seen it for audio and music spectrum, right? So let me know how helpful this is for you. And if there's something you'd like me to try out, feel very free to let me know. All right. So if you have subscribed already, I must say thank you very much. If you have not subscribed, feel free to subscribe because, of course, if you don't do that, you'll be missing a whole lot. And don't forget to hit the notification bell so you can always get alerted each time a new video is released. Then, having done that, you want to take it a step further. You want to become a member of the channel by clicking on join, and you see some 3 levels of membership that comes with some. Each one comes with some very special privilege. So you want to avail yourself of that benefit for sure. And let's see how we can work together. I mean, build this community together. All right. So ultimately, don't forget to like, share, comment so that more people can have access to the great content I have going on here till I come your way again. Keep doing Python right, keep doing data right, keep doing maths right. And like I said, this is about the last video on spectral analysis, except something else comes up and I have to make another video. It's been a nice time doing this. It's been a learning process, a very interesting learning process for me as much as it is for you. Till I come your way again, keep doing spectral analysis right. Bye.